An electrocardiogram, or ECG, monitors electrical activity in the heart. Electrical activity arises spontaneously in the heart at the sinoatrial node. It then spreads through the atria, causing them to contract, and goes on to the atrioventricular node at the top of the ventricles. From there, the signal passes down conducting cells in the interventricular septum, then spreads out through the ventricles. The signal reaches ventricular muscle cells as an action potential, which can be recorded by placing an electrode in the cell. Muscle action potentials look like this. Each action potential consists of a large and rapid depolarization of the cell membrane that lasts around 200 milliseconds before decaying back to baseline. Each impulse from the sinoatrial node generates action potentials in the atrial muscle and then the ventricular muscle cells. The electrocardiogram monitors the global signal generated by action potentials arriving simultaneously in all the muscle cells of the atria or ventricles. To record an electrocardiogram, metal electrodes are attached to a minimum of 3 points on the surface of the skin. In the simplest case, electrodes are placed on each arm. One is a positive electrode and the other is negative. A third electrode is placed on the ankle. It is a ground or reference electrode that provides a baseline against which signals at the other two electrodes are compared. Wires connect the electrodes to a measuring instrument known as an electrocardiograph. Each time action potentials arise and travel through the heart, they generate currents that spread through the body's tissues to the electrodes on the skin. The electrocardiogram detects voltage differences between the positive and negative electrodes, and this is plotted on a graph as voltage against time. When measured from subjects with a healthy heart, the electrocardiogram has this characteristic shape. This is a schematic of a typical ECG trace during one beat of the heart. In between beats, when the heart is in diastole, no action potentials flow through the heart. This quiet period is represented by the isoelectric line, which shows the minimum difference in voltage between the positive and negative electrodes. Deflections in the trace are measured relative to the isoelectric line. Three characteristic features are apparent. The first bump in the trace is called the P wave. It detects depolarization of the atrial muscle as action potentials arrive from the sinoatrial node. It is followed, after a delay of about 100 milliseconds, by the QRS complex. This part of the trace detects depolarization of the ventricular muscle. The QRS complex is larger than the P wave because the ventricles have a greater mass than the atria, with many more muscle cells contributing to the signal. Note that there is no signal from the sinoatrial node before the P wave. That is because the sinoatrial node is very small, with only a few cells producing action potentials. The resulting currents are just too small to be detected at the surface of the body. The QRS complex is followed after a delay by the T wave, which represents repolarization of the ventricles. You may wonder why ventricular depolarization and repolarization are detected as separate events in the ECG when they are continuous in an action potential. The reason is that the ECG detects changes in voltage between the two electrodes. During the plateau phase of the action potential, there is little change in membrane potential, so when depolarization is complete, the ECG returns to the isoelectric point. When the ventricular action potentials reach the repolarization phase, the voltage between the positive and negative electrodes on the skin changes again, giving rise to the T wave. This is a useful feature of the ECG because the period between the QRS complex and the T wave gives a measure of the action potential duration. Additional features of the ECG are crucial for diagnosing various cardiac conditions. The time between the start of the P wave and the start of the QRS complex is known as the PR interval. It reflects the time it takes for action potentials to travel from the atria, through the atrioventricular node and into the ventricles. The PR segment is a flat part of the trace on the isoelectric line between the end of the P wave and the start of the QRS complex. It represents the time when action potentials are travelling through the atrioventricular node. The period from the start of the QRS complex to the end of the T wave is known as the QT interval. It represents the total time taken for ventricles to depolarize and repolarize, in other words, the action potential duration. The ST segment is a flat isoelectric part of the trace between the end of the S wave and the beginning of the T wave. It represents the time between completion of ventricular depolarization and the start of repolarization. In other words, it's the duration of the ventricular action potential plateau. Another measurement is the RR interval, which is the period between each cardiac cycle, from one ventricular depolarization to the next. It gives a measure of heart rate.